So far, our search for maxima and minima has focused on using critical points. However, there's a single category of potential extrema that cannot be detected with critical points. If you're trying to find the extreme values of a function on an interval, these points occur at the endpoints of the interval. For example, let's say that we're trying to find the global max and min of the function f of x equals x squared on the interval -1, 2. Graphing the function on this interval makes it pretty easy to spot the largest and smallest values of the function. In red here, I'm also going to draw what the function would do if we hadn't restricted it to this interval. You can see that x squared has a single critical point when x is equal to 0. This is the only point where the tangent line is horizontal, and it happens to coincide with the global minimum. The global maximum, however, occurs at x equals 2. And it's not too hard to see why it's not a critical point. If our function had not been restricted to this interval, this would not be a potential maximum. Rather, it's only because the function was cut off as it was growing that x equals 2 is a potential maximum. So in this case, one global extrema was a critical point, but the other was an endpoint. And, as I mentioned, the reason for that is that generally endpoint extrema do not need to be critical points. So, how do we deal with this? The answer, brute force. An interval only has two endpoints, right? The left side and the right side. So we can just plug these endpoints into our function and return their values. Then we compare these to the results of our interior critical points to find the global max and min. Now, of course, this won't generalize when you start doing optimization problems in higher dimensions, but for now, we're just grateful that we're working in a single dimension. So let's take everything we've learned and let's apply it to the following function. We have here a quartic function, which we want to optimize on the interval -2, 3. Let's work on the interior critical points first. Differentiating f gives us this cubic, which we can factor into linear terms as so. The critical points are the roots, which we can read off easily as -1, 1, and 2. Let's use the first derivative test to classify these critical points into maxima and minima. As polynomials are pretty easy to differentiate, now would actually be a really good time to use the second derivative test, so you can give that a try if you like. Note that if you set this table up correctly so that the linear terms occur in the same order as the roots, it's actually pretty easy to fill out. Each time you move past a root, the sign of the next term flips. Thus we can read off the increasing and decreasing intervals for f. The first derivative test then tells us that -1 is a minimum. We're going to need the actual value of this minimum, so I'm going to compute it while I'm here. Similarly, x equals 1 is a maximum, and the value of f at 1 is computed as so. Finally, x equals 2 is a local min, and we can work out f of 2 to get the value of 18. Now that takes care of our interior critical points, so let's move to the endpoints. These can be maxima, minima, or neither, so the only thing that we can do is to work out the value of f at each of these points. On the left-hand side we get 50, and on the right-hand side we get 55. And we're done at this point, but let me summarize what we found in a table. The critical point minima are as follows. There is a single critical point maximum, and as endpoints can be either, I'm going to give them their own column. The global minimum and maximum are those points which have the smallest and largest values of f respectively. Thus, the global minimum occurs at the point -1, -9, and the global maximum occurs at the point 3, 55. So be sure to remember to check your endpoints because it's really easy to forget that these can be potential maxima and minima.